Hello, my name is Mohammed Bakr Sikal, a PhD student at the Khdr Institute of Technology, and today I will present to you our recent paper, Thermal and Cache-Aware Resource Management based on ML-driven cache contention prediction. With the continuous demand for computational power, parallel computing on many cores has helped increase the overall system performance. However, the heat transfer between multiple running cores can lead to the creation of hotspots on the chip, thus leading to thermal violations that can impact the reliability of the chip or even permanently damage it. Also, simultaneously executing applications contend for the shared resources of the chip, like the last level cache. This contention results in execution slowdown for the running applications, which can lead to performance constraint violations. Clustered many-core systems can reduce chip-level contention by sharing the last-level cache only among the cores of the cluster. This reduces the chip-level contention, but at the same time does not help with contention between applications running in parallel on the same cluster. To this end, recent state-of-the-art system-level resource management techniques attempt to reduce this cluster-level contention by proposing to co-map memory-intense and compute-intense applications in one cluster. While this approach indeed reduces the contention at cluster level, it might lead to higher chip temperatures due to the high power consumption of compute-intense applications. To better understand this problem, let's look at the following motivational example. Before we dive into the details, let's look at the system architecture first. We simulate a clustered many-core system where each cluster has 8 cores that share one last-level cache, and each core has its private L1 and L2 caches. For the sake of simplicity, in this example, we consider a system of only 2 clusters. As you can see, each cluster has 4 occupied cores and 4 available cores. 2 applications, X264 and BuddyTrack, from the Parsec benchmark suite are running each on a separate cluster, both at the same frequency. Both applications have 4 threads, and each of them is running on a core on the cluster. X264 is a memory-intense application, which is reflected in its high number of last-level cache accesses and relatively low power consumption. BuddyTrack, on the other hand, is rather compute-intense, which is reflected in its low number of LLC accesses and high power consumption. A new application, CES-KIT, arrives to the system, and we want to know to which cluster we should map it. There are 2 options. We can either co-map it with X264 on cluster 1 or with BuddyTrack on cluster 2. Now, let's see the implications of each option. When we co-map CES-KIT with the memory-intense X264, and due to cache contention, CES-KIT finishes its execution in 95 milliseconds with an average cluster temperature of 72 degrees Celsius. In the other scenario, when we co-map CES-KIT with BuddyTrack, CES-KIT finishes its execution in only 83 milliseconds, but the average temperature of the cluster reaches 81 degrees Celsius. As we can see, if our goal is to maximize performance, cluster 2 would be the best option, as BuddyTrack is not memory intense and did not slow down our new application CES-KIT. But this came at the expense of a high temperature of 81 degrees Celsius. On the other hand, if our goal is to minimize temperature, then cluster 1 could be the better option, as X264 is low power and the co-mapping results in a low cluster temperature. But we should also accept that our new application will suffer from the contention-induced slowdown due to the memory intensity of X264. In fact, we are the first to explore this trade-off with the goal of minimizing temperature and their performance constraints. But this requires that we are able to predict the cache contention-induced slowdown between applications on a cluster and the temperature resulting from this parallel execution. While we can predict temperature using the well-established RC thermal model, contention prediction remains a challenging task. The first challenge comes from the fact that slowdown should be estimated at the arrival time of applications before performing the actual mapping. This is a problem because at the arrival time of an application, its characteristics are still unknown to the system. One solution would be to profile all application combinations at design time, but that is not really feasible since an application's memory intensity varies throughout its execution. To better understand this, in this figure, for instance, we can distinguish between multiple phases in the execution of Canil when it is running alone on a cluster. While at the beginning we can see a low number of last-level cache accesses and misses, later on, during its execution, the application shows a significant increase in the number of cache accesses compared to the previous phase. Consequently, another application that is co-mapped with Canil on the same cluster will suffer differently if it arrives at the first phase of Canil compared to the second one. The number of these combinations of applications and all their possible arrival times is exponential and makes the option of design time profiling unrealistic and unfeasible. To gain more insight into the challenge of slowdown prediction, let's look at some examples. This table shows the slowdown incurred by some applications from the Splash2 benchmark suite when co-mapped on the same cluster with other applications. The bars show the suffered slowdown by application A due to application B. There are many observations that can be drawn from this table. The first observation is that Stream cluster is not slowed down by any application, while it slows down all applications it is co-mapped with. Secondly, different application pairs show different slowdown behaviors. LUcont, for example, suffers a slowdown of 20.8% from Stream cluster and 27.2% from Kolsky. From this example, we might conclude that Kolsky can cause more slowdown to an application than Stream cluster. However, if we look at LUncont when co-mapped with the same two applications, we can see the opposite trend. This time, LUncont suffers a slowdown of 22% from Stream cluster, but only 17.4% from Kolsky. These different behaviors show that slowdown prediction is indeed a complex problem. To tackle this complexity, we employ a neural network model to predict the execution slowdown of applications. Our contributions can be summarized as follows. We design, train, and employ a neural network model to predict the slowdown in the application execution, and we propose a thermal and contention-aware resource management technique, TCRM, that jointly determines application-to-cluster mapping, thread-to-core mapping, and the required VF levels in order to minimize temperature while satisfying performance constraints of applications considering the slowdown induced by cache contention. Now, let's look at an overview of our proposed technique. At a high level, our work consists of a design time phase and a runtime one. At design time, from simulation traces, we first generate training data to train our neural network. At runtime, the neural network model enables our technique to perform its tasks of mapping and VF selection. In the next slides, we will look at the details of each phase. At design time, we run simulations on the Hot Sniper simulator with applications from the Parsec and Splash2 benchmark suites, both alone and in pairs at all supported frequencies. Meaning that for each pair of applications, A and B, we first run A and B alone on separate clusters, then in parallel on the same cluster. We have shown previously that the memory intensity varies throughout the execution time of applications. Consequently, if application B is already running on the cluster, then depending on the arrival time of application A, both applications will suffer different slowdowns. We refer to this shift in the arrival time by delta R. In our experiments, we use only 2 applications and 2 values for delta R. However, as it will be demonstrated later, our technique is able to generalize to any number of applications and delta R values. Also, the shared execution time where both applications will be running depends on the value of delta R. We refer to this period of time as R shared. Now, with the alone and parallel execution times of application A at hand, we can compute the slowdown it suffers from B, which is the label that our model will try to predict. As with any machine learning model, the question is, what are the features of the 2 applications A and B that have the best predictability of this slowdown? To find out, we extract the recorded performance counters at the period of time that corresponds to R shared in the alone traces of both applications. These performance counters contain different memory statistics, like DRAM reads and writes, cache accesses, cache misses, so we use lasso regression to find the performance counters with the best predictability of the slowdown label and the Pearson correlation matrix to analyze their correlations. Our training data now contains a list of features extracted from the alone traces of A and B, the frequency at which they were run at, and the label, which is the slowdown suffered by A due to B. This training data is then split into training and test datasets, which are used to train the neural network model. At runtime, when a new application arrives, TCRM first tries to find all eligible clusters where the new application can be mapped. For each cluster that can potentially host the application, our technique needs to check whether there is a VF level that the cluster can run at and at which all running applications can meet their performance constraints. Here we can see that application A has 2 threads, which means it requires 2 free cores since we are using the 1 thread per core model. Obviously, cluster 2 and cluster 4 are directly eliminated as they do not have enough cores to host application A. Cluster 1 and cluster 3, on the other hand, are potential clusters for our application. To verify the eligibility of the 2 clusters, the technique first extracts the features we selected before from the alone traces of each application during the period of time that corresponds to R shared. Then the NN model is queried with the current VF level of the cluster and the extracted features. Cluster 1 in this example is running at frequency F1, so F1 and the extracted features are passed to the model, which returns the slowdown that application A will suffer due to the already running applications on the cluster at frequency F1. We know the performance constraints of application A, so the technique verifies whether this will result in a performance constraint violation. If it is the case, we keep testing the other supported frequencies until one of the frequencies satisfies the performance constraints of the application. In this case, F3 is the minimum frequency that would allow all applications on cluster 1 to meet their performance constraints. This frequency is saved and the next cluster is checked as well. Let's assume that for cluster 3, F2 is the minimum frequency that the technique has found. At the end of this step, we know that cluster 1 at frequency F3 and cluster 3 at frequency F2 are eligible for hosting application A. This step does not only guarantee that performance constraints will be satisfied, but it is also a step towards temperature minimization, since we chose the minimum VF level that makes a cluster eligible. To further minimize temperature, we need to select, given the eligible clusters that we have found, the application to cluster, and the thread to core mapping that will result in the minimum chip temperature. For that, we use the well-known RC thermal model to estimate the steady-state temperature that will result from co-mapping the newly arrived application to each of the eligible clusters. For the already running applications, we can compute their average power consumption. For the newly arrived application, we can compute its average power consumption from its alone traces. Here, cluster 1 has 3 available cores, and application A only needs 2 of them. So the technique tests all mapping combinations and saves the one that results in the minimum chip temperature T1. For cluster 3, since it has only 2 cores that are available, these represent the only mapping option possible on this cluster, and the technique saves the predicted steady-state temperature, in this case, T2. Assuming that T1 is the lowest predicted temperature, cluster 1 becomes our winner with the selected thread to core mapping that would result in temperature T1 at frequency F3. Now, when one of the applications on a cluster finishes its execution, the technique searches again for the minimum VF level that will satisfy the performance constraints of the remaining applications on the cluster to further minimize the temperature of the chip. Now that we have seen the details of each phase, let's look at an example that demonstrates our technique in action. This figure shows the number of LLC misses of FMM, an application from the Splash 2 benchmark suite when running alone on a cluster. As mentioned previously, we noticed a number of phases throughout the execution time of the application. These phases are characterized by highs and lows in the number of LLC misses of the application. We consider that applications can meet their performance constraints when running alone on the cluster at 2.4 GHz. Now, let's see how our technique reacts when a new application, CES-KIT, arrives to the system and will be co-mapped with FMM on the same cluster. First, we can see here at the arrival time of CES-KIT that FMM is in a phase where it is exhibiting a very high number of LLC misses, reaching around 80,000 misses per millisecond. In this case, TCRM decides to boost the VF level of the cluster from 2.4 to 3 GHz. This frequency should allow both applications to meet their performance constraints. Indeed, after around 90 milliseconds, CES-KIT finished its execution, satisfied its performance constraints, and left the system. Note here that since FMM is now again running alone on the cluster, TCRM decides to throttle down the cluster back to 2.4 GHz. At around 108 milliseconds, a new instance of CES-KIT arrives to the system. However, this time, FMM is showing a much lower number of LLC misses compared to the previous phase. Consequently, TCRM only boosts the VF level of the cluster to 2.6 GHz this time. A few milliseconds later, FMM finishes its execution after satisfying its performance constraints and leaves the system. Again, since CES-KIT is now running alone on the cluster, our technique decides to throttle down its VF level back to 2.4 GHz. As expected, CES-KIT also meets its performance constraints and leaves the system at around 280 milliseconds. We can see that our technique has successfully adapted to the different execution phases of FMM and has selected the right VF levels that allowed all applications to meet their performance constraints. To evaluate our technique, we run simulations using the Hot Sniper simulator on a many-core clustered architecture with 8 clusters, each having 8 cores. Each core has 256 kilobytes of private L2 cache, and each cluster has 8 megabytes of L3 cache. The frequencies range from 1 GHz to 4 GHz with steps of 200 MHz. As we have mentioned previously, we are the first to explore the trade-off between cache contention and temperature. This means that state-of-the-art techniques only tackle each problem individually. Therefore, we compare our technique against co-RM a combination of a thermal-aware application mapping technique and a cache-aware and neural network-based DVFS technique. For our evaluations, we create workloads of 20 randomly selected applications from the Parsec and Splash2 benchmark suites. To demonstrate that our technique can generalize to the different arrival rates of applications, we run each workload at 5 different arrival rates sampled from a Poisson distribution. Like in the previous example, we set the performance constraint of applications as their alone execution time at 2.4 GHz. And now, let's look at the results of these evaluation experiments. This first figure shows the normalized response times of applications at each arrival rate for our TCRM and the state-of-the-art technique CoRM. We will use these box plots for all result figures, where the whiskers show the distribution of the reported values in 5 groups: the minimum, the first quartile, the median, the third quartile, and the maximum. In terms of performance, we can see that both techniques manage to satisfy all applications' performance constraints. But in the case of CoRM, applications finish way before their performance constraints, thus showing a slack time of up to 31%. Our technique, TCRM, on the other hand, shows minimal slack time, and applications always finish very close to their performance constraints. This is a result of the high accuracy of our slowdown prediction model and due to the fact that TCRM only considers the shared execution time of applications. On the other hand, CoRM, the state-of-the-art technique, considers the full execution time of applications and not only the parts where they run in parallel. In terms of chip temperature, TCRM results in a lower temperature at all arrival rates, with up to 24 degrees Celsius difference compared to CoRM. This is mainly due to the fact that our technique chooses lower frequencies and also tests more thread-to-core mapping options that further minimize temperature. Finally, CoRM almost always selects higher frequencies than our technique. This difference can be up to 35% at arrival rate 20, for example, which explains the long slack times and higher chip temperatures we have seen previously. Our technique is able to achieve better results thanks to the high accuracy of its prediction model that allows it to select the minimum frequency that satisfies the performance constraints of applications. To conclude, we looked at TCRM, the first resource management technique that explores the trade-off between cache contention and temperature. With an overhead of only 1% of the average execution time of applications, we have seen how TCRM manages to significantly reduce the chip temperature compared to the state-of-the-art while satisfying the performance constraints of all applications. This is mainly thanks to the high accuracy of our neural network prediction model, which achieves a very low root mean squared error score of only 2%, while maintaining a low inference overhead of 3 microseconds. Thank you for watching this presentation video. Check out our paper to know more, or approach us directly if you are interested in our work.